Hello and welcome back to another episode of Effective JaRu, the series where we read effective Java and try to apply the individual items to idiomatic Rust, if possible. So generics, I took my time really and took a few days off, I suppose, and did other things, but read this book and especially the generics part from time to time. I found it very discouraging in a way. Because of the way generics are implemented in Java. I do understand that it is what it is, and I think it's still good to have, but it's not without its, well, let's say, issues that are also mentioned in the book partly. And I think when you use generics, what happens is that the compiler will not be your friend anymore. Mainly due to Java's unholy way of stating compiler errors, right? So if you are used to Rust, then you will probably not find the Java compilation errors very useful. Let's dig in. Don't use raw types in new code. So there's nothing like a raw type in Rust, so we can't apply this at all. A raw type basically means that if you have something like a set, for instance, and you use a set without any type parameter, then it's called a raw type, or a list, for instance. Raw types are just to support legacy code, if you think about it, because previously everything was a list that contains only objects. Now this is handled by the raw list, and what you would want to do is to have a list of a certain item type, a certain class type. And this is how you would name it. So a list of E is then, let's undo this. Can I undo this? No, undo. There's no undo in books. Well, F you. So it's a bit weird that, you're used to undo, but probably it's not needed most of the time anyway. So that's as far, that's easily understood. There's more about generics. We might just have a look here and see what code examples there are. Unfortunately, there's no real good code example for issue 23. Or is there? Oh, there is. Okay, that's this one. Sorry. I take it back. Item 23. But most of the stuff you see here is basically just example code that has no actual code associated with it in the book, and the book's source code repository. Yeah, I think the main idea about generics is that you're getting more type safe, because at compile time, the type will be checked for you statically. It's a compile time check. But at runtime, you get exactly the same bytecode that you got before, and casts are inserted for you by the compiler. The compiler can just prove to some extent that the cast is going to be safe. But thanks to the support for legacy code, you can do things that will remove the type safety from your code at compile time even, or make it ambiguous so that your compiler cannot understand anymore what's going on. I think these examples here kind of nicely show the examples here. Basically, they nicely show what the issue can be there. I'm just sneaking through the book here to see possibly more. What else is there? Is this just, did we miss an item here? No, it's multiple pages of gorgeousness when it comes to generic. What else? Yeah, it's probably quite interesting to read this. I mean, I read it, but probably I forgot most of it already. There's also it's really, to me, it seems like a half-baked approach, right? They could only do it as good as they could do it with Java and without breaking all the code that was there. So again, I think it's good to have, but yeah. So this is basically the syntax that you can use to do these things. Oh, look at that. I double clicked it. So I have a list of strings, and can I also, yeah, it fits the screen. Good. a list of strings where this is the type parameter. The generic type would be E, formal type parameters. It's good to have a common vocabulary to talk about. I can't promise you that I will be able to stick to this vocabulary unless I read it from the book, and maybe at some point it sticks, but for now I don't see this coming. Yeah, I will use generics too in Java if I write it, because it's useful, and it's much better than having to upcast to object all the time and then have an indeed unsecure downcast. So yeah, let's have the compiler test or check that for us, but that's really as far as compiler checking goes. Unfortunately, this whole syntax will make your code even more verbose. And really, I already start hating the world if I have to program this. Yeah, so let's have a look at this example here. The raw class, it's really just a bunch of static methods here to show what the difference is. We can try to build it. And you see all these errors showing up, which is, you know, it would be so useful if it wouldn't use the whole path all the time, or if it would put that to the next bloody line, man. Man, what the heck? So warning, raw types, found raw type list. Yeah, so unsafe add here. Missing type arguments for generic class. So it really wants you to be explicit about this. So that's legacy code that you shouldn't write anymore that is still supported, but you know, you get warnings at least. Warning, unchecked call to add E as member of the raw type list. Okay, what does it mean? We call add, but we are in an unchecked environment here. I think that's this line. So basically we just add an object to something that previously was known to be a list of strings. See? What else? Raw num elements in common. Missing type arguments for generic set, where E is a type variable. So it's the same thing as before, just with sets. And this is what you probably want to do in a naive approach. This basically just means that you don't care about the actual type that is in there. And I don't know where the difference is in detail, except that you don't get a warning here. Yeah, so that is that. There's no way I can show this in Rust. I mean, Rust doesn't have that. In Rust, you are always type safe. You cannot opt out of that. Generics are part of the language, have been from day one, which is great because that way there's no weird legacy stuff that had to be supported, right? So we can be lucky in the Rust world, really, that it's such a modern language from the get-go. I'm sure in 5 years from now we will look at the same issues with legacy stuff that looks awkward and still has to be supported, or the community decides to really go 2.0 and cut it all off to have the most beautiful, most elegant language possible, and then you just say, well, some projects will not compile with Rust 1 anymore. But that's really just that. Also splits the infrastructure in half of those crates that would support Rust 1 and those who don't, which is what we have seen in Python. So it's also something you probably don't want. So yes, we are still lucky in the Rust world, but it's also younger, let's say. So on the right side, you see, I think there was an example for nested types here, which are not available in Rust. But I wanted to show you how you would do this. So if you want to have a builder and an iterator, for instance, in Java, you would have nested types going on. In Rust, you don't. But what you obviously, and something I want to show now that we are at generics is how generics are used to implement the iterator type. Because usually we have been very specific about the foo type that we want. But when implementing iterator, we do something very, very cool. We do, we have a generic type parameter here. Or let's just say a type parameter here, t, which says that our inner value here should be a, what just happened? should be a borrow of foo. And when we implement it, we just carry on and say, well, we want to borrow foo, we want to borrow foo, and the only difference is that if we want to use inner, we first have to borrow it. This is what the borrow trait does. And the great thing is that borrow is implemented for basically all types generically, and this means that if you have and here it comes, if we have a actual borrow of a foo, then we can pass it to iterator new, similarly to if we have the actual foo. So this is moving foo into the iterator, which is why it's called into iter. This will definitely consume the foo instance that we had, move it into inner, and then it's there, basically caught there, right? Then we cannot do anything with the original anymore. This is awesome to have move semantics even for iterators, because that kind of consumes the item. Here it doesn't make so much sense because it's copyable items, but if these were movable items or non-clonable, non-copyable items, then you would benefit from that, because then you could actually move these fields out of their source structure with an iterator that owns the values. So that's also called draining when you are in a vector environment. So you can iterate over vector elements, and you don't just get a borrow to a vector, but you do get the element itself, taking it out of the vector. And you can easily do this yourself with one code base and a simple generic, which is borrow. So borrow is really, really useful for that kind of stuff, even though this example is somewhat contrived. So we could actually do that. We have a pub struct non-copyable. So this can't do anything. We might wanna, no, we don't have to. I don't think we don't have to do anything here. We can make this non-copyable now. A, B, and well, let's make it an enum then, to have at least distinct values here, and maybe make it even comparable. 1, 2, so we have 2 values in there, but this thing is non-copyable. We will derive partial equality and debug though, so that we can use it better in our code. Sorry, I have to. That's odd. My weak programmer body doesn't want this constant intake of fresh air through the windows. That's what I interpret into that sneezing. So we have non-copyable here. This can have one of 2 values now, one of 2 states basically. No, we can basically just change this around a bit. And yeah, the builder is really just about the type, is it? And yeah, we consume the builder, put back self inner, so that's fine. We don't clone anything there. And now our item is non-copyable, and now things will get a bit different, that's for sure. This should still work, except for, oh, actually, wait, this should still work except for in one case. Yeah, let's see what the item type is, because the item type is actually must actually now be a borrow to a non-copyable. And I wonder, I have no idea actually how I will be able to change this to something else. You know, this non-copyable stuff, I think I wouldn't do it in this example, but it can be something that is supposed to be explored, because in fact I would wanna alter this now based on whether we have an actual borrow of foo or we own it, right? But I don't see how that would work now. But anyway, funny games, we might play them later. So that should still work. I think the test I adjusted, so we have into iter here. The thing is, we cannot use f anymore now. So if you wanted to assign it, this should fail. Yeah, it will fail. See, because we have tried to use a moved value f. In that case, the other stuff just has been ignored because it was worth being ignored. Yeah, so that is that. Let's keep looking. How much time have we spent? 15 minutes. Yeah, we can as well. See what else there is. Eliminate unchecked warnings. Yeah. So plenty of examples are here that show you how raw types will trigger unchecked warnings and certain weirdnesses that can happen that I don't truly understand, where the compiler actually can't tell you that anymore. So if you do casts yourself that have generic types in them, then usually you get a compiler warning because the compiler can't check this at runtime, right? At runtime, we lose all the generic type information, just not there anymore. So these casts translate to something at runtime that is probably not there at all. I don't know. And that's what you get as a warning. So, suppress warnings. That's interesting. So there is an annotation here that allows you to suppress the warning produced by the item that you annotate. So this can be a variable or a statement. I don't know. I never tried it myself. But that's, I think, generally how that works. And there is no item 24, unfortunately. Maybe we make one ourselves. And yeah, obviously, or something that I read from the book all the time is that here, eliminate every unchecked warning that you can. So does it mean some warnings cannot be eliminated? And if so, why is that? All warnings should be warnings that are based on something that you can fix. If it's a warning that is just happening because Java itself is so flawed that it really can't tell, then I think this is broken, right? This is inherently broken. This is something that I read in the lines of the generic chapters so far. Generics in Java are tagged on and are, better than without them, or you are better than without them, but you have a lot of bulk that you have to carry around with you when you want to use them, actually. And I'm not sure, also with the syntax, because this seems simple here, or your definition like this seems simple, but it can be arbitrarily complex here. So this stuff, when you start to have bounds, for instance, then what's in here gets extremely long, or can get very long. And in Rust, you use where. We have just had that. Let's bring it up again. item22lib. So where is your friend? Because where allows you to just have your type parameters, and then in a separate line or somewhere else, you basically define your bounds, which can get very wordy, I'd say. And in Java, you don't have that. In Java, you have to put it here, which is similar to doing this in Rust, right? So then you would have to cut the foo here. And as you can see, it gets harder to read if you do it that way. And in Java, you are destined to write code that is hard to read when you are using generics. If you can't eliminate a warning and you prove that the code that provoked the warning is type safe, then, and that's already fail, right? That's already fail if you come from Rust or if you are used to Rust, because you can't prove that, can you? I mean, you can prove it in a comment that maybe nobody reads, but you shouldn't do it. It's and you shouldn't be forced to do it because there's no other way to fix it. That's what I'm saying. Always use the suppressed warning annotation on the smallest scope possible. Yeah, that's just common knowledge in a way. If you think about it, you don't want to suppress other warnings that you might actually be able to fix. So that makes sense in any case when you want to suppress a warning of a compiler. So what else is there? Adding local variables to reduce scope of compressed warnings. So some tricks to get a new scope for stuff. I'm not sure if you can apply suppress warnings to a scope that you introduce, not through an extra variable, because that variable, that intermediary that costs you, right, it's another binding. I don't know if the Java compiler is able to compile that away or to optimize it away, but I would not assume such things. So this is another binding. In Python, for instance, this would cost you an access to the locals array of the locals hash map of the function, right? I don't know how that works here and how far you can reflect the variables on the current stack frame or in your current function. That is, I have no idea. So if you can't reflect these, then this would mean that this is in fact efficient. But hey, it's Java. I don't think Java is very efficient at all, because it is what it is. But yeah, just have to shut up and live with it, I guess. So every time you use an suppress warnings unchecked annotation, add a comment saying why it's safe to say so. Well, that explains itself. It's just sanity. It's just about code maintenance. It's required because other people must be able to understand your thinking behind suppressing a probably legitimate compiler warning. Probably. I mean, do you trust the compiler that whose warnings you cannot fix? I'm not sure if I want to trust that thing then. So prefer lists to arrays. It's about the covariance, right? I always forget. I think arrays are covariant, whereas lists are not. And this covariance can lead to losing the compile time type checking if you do that a lot, because this would allow you to assign or to basically upcast an array. I think having covariance in arrays is a bad thing, but still, you can upcast array of a certain type to array object, for instance, and then you can add anything to the. Oh no, actually that's not. Oh, actually you can't. This is still checked, but it's checked at runtime, right? Whereas the other stuff is checked at compile time. I think that's the difference. Ooh, thank God. See, I was about to memorize that you can then add anything, but it's still runtime checked. Good. That's a good thing. Also shows you how expensive it is to do anything in the Java world, because it's always, if in doubt, it's runtime checked. And I'm not sure what happens in this case, if this is still runtime checked. I think it is. Maybe it's not. Maybe the compiler can deactivate that in case he can statically prove that this is correct. But yeah, generally I think there are certain costs involved thanks to the constant type checking and the constant null checking as well that happens, right? Each of these reference types, they could be null, which is also something I find quite terrible. But hey, there are no optionals, I think, unless you have Java 8 or something, which might have added them. Let's look at it real quick. Java 8 optional. Show me. Optional T. Whoa. So it is a utility type. Look at that. A container object which may or may not contain a null value. If a value is present, it will return true, and get will return the value. Okay. What can it do? Construct itself, and then the typical ones, if present, it has a consumer. Oh yeah, that's just the callback, right? That's the Java way of having a callback. So if present, call this, or else. So you have a bit of this. Yeah, so that's unwrap basically. Unwrap or is this. Yeah, so something to get used to. I think it's a poor man's optional if you know the Java one. I always have to compare it, and I do not like Java. This must be hard on the ears of any serious Java programmer, but it's really no. I had my reason to stay away from this for as long as I can think, and now I can't anymore. But I will do my best to make sure people know about alternatives. So, what else is here? Yeah, so compile time checking. Oh yeah, and this is, I mean, this was crazy. I was, this kind of happens or goes into the realm of concurrency. And of course, Java has no notion of this. You have a few primitives. You probably have all the primitives in the world to do synchronization of your data or to synchronize various threads. But it's all unchecked, basically. It's all done at runtime, right? So the only one who probably maybe knows about these things is the programmer, and we all know that these guys don't know about anything if the program is just complex enough and basically is more than one screen. And even then, things can be subtle when it comes to concurrency, and having a compiler that is not able to check the basics, then you're doomed. And what I find interesting is this thing here. So apparently you can take variables into a synchronized code portion. So obviously these can only be executed by one thread at once. This is what I see from this, even though I have no idea how this really works, but that's what I would interpret into these lines. And why is this happening? Why is all of a sudden concurrency a matter here? And, this has to be documented as all but just part of the documentation. Is nothing the compiler would check for you. In Rust, all of this is checked. Your code will not work in concurrent situations unless it's accessed in a read-only fashion. And unless you don't have interior mutability, so the compiler will check that, and you're sure. You don't have to write about this in the documentation anymore. It's the code that documents itself in terms of whether or not it can be used in a certain way by multiple threads at once. And this is, once you have had this, you don't want to go back because it's so internal that this is working with multiple threads or not. Generally, I would assume that nothing works in multi-threaded situations, especially with the singletons going on in Java and static mutating methods or static methods in general, and static non-final or static fields, right, that can be manipulated. So all of this is really, really difficult to get right. And this is also something, that was the next thing that made me want to stop reading this. List to array. Oh, look, locks list internally. Oh, did you know that? So this snapshot is now locked. Is it thread safe now? Or what kind of locking is this? Or is it just a runtime check that prevents this to be called again when there is a snapshot? I have no idea. You have to read this in the documentation and understand it very well. Generally, I think you would do well if in Java, if you would just not share data, but you communicate. Basically, you send copies around of the data. And that way you can be sure that no two threads access and mutate the same data at the same time. Anyway, I don't want to write such code. With Java, I don't want to write concurrent code because I'm sure I get it wrong. Unless you have a framework maybe that will make sure that you only communicate. You only share by communicating basically and not share through data. And that your types support it, but you can never be sure. And from that, weird, hard to debug errors can arise, and I'm already afraid of this. So, multi-threaded Java code? I try not to do that. So, what else is there? Favor generic types. Yeah, so basically everything that is not generic is legacy. And with generic typing, you can make your APIs more statically easier to use, because the user doesn't have to statically. Oh, by the way, we have an item 25 here. Doesn't have to insert the castings himself anymore. Let's have a look at item 25. We have a function and reduction. Okay. So we are generic. We have generic statics here, and I think this is only, you have to see that this is actually a static type, right? A static class, and it's just there to show off these functions here. But in Java, again, we are unable to have anything without a class, which is adding more boilerplate to everything. Thank you, Java, for this. So let's see. So static final functions, function integer. So that, where is that function coming from, by the way? Maybe that's, but still, where is it coming from? Do we have a function class? Here it is coming from, sure. Function, that's a functor. It's like an interface of objects which have an apply, which is like execute, right? And you kind of hard code it to be what you need in a generic fashion, though. And then you can have anything you want and specialize it. Yeah, well. Also here, the capabilities of your type, it's nothing you can put into the bound of what you want. It's probably checked at runtime then that this actually is there. I don't know how that works, actually. So these public finals are just anonymous implementations of that interface, so that you can reuse these instances in the reduce call here, which is also fully generic. And here it's as simple as it gets. So I think this is a good example for how generics can be useful, and I actually like it because it's still simple and definitely better than casting the stuff yourself all the time. So from that point of view, as I said initially, I think generics are a blessing for the Java world if they wouldn't be so tagged on. So 26 first technique. What's this? Yeah, you know what? I think now that we are at item 26 here, favor generic types, we might even make a cut here and go ahead in another session with the other items. Maybe write some Rust code again. Thanks for watching and have a good day.